Hello everyone. This week I wanted to focus on creating a single voice harmonizer in Grainflow. This will help understand how to get things going in real time and also will provide you with hopefully a useful tool. Next week we'll be expanding the harmonizer to work with multiple voices, but for now we're going to start with just one. So the first thing we're going to do is create our Grainflow object. Give it a buffer name. So we'll just call it Harmon. And I'm going to get 4 grains. 4 grains is a nice amount to make it sound really smooth. You can get away with 2, which would be like your traditional pitch shifter, is basically a 2-voice granulator. But we're going to do 4 voices because it sounds a bit nicer. And we're also going to need a buffer. We're also going to name it Harmon. I'm going to make it 5 seconds. The amount of time the buffer is compared to the grain size is going to determine how much pitch shifting can do before overrating or going before the buffer if we're going slower. I've found 5 seconds tends to be plenty. And then we'll make a Grainflow record, or util record, with the same buffer name, Harmon. I'm going to connect the first outlet of the record to the traversal inlet, which is the second one of Grainflow. All right, so we have that set up, which is great. I'm going to create a Grainflow waveform so we can see what's going on. Connect that to the second inlet, and it will set the buffer when we turn it on. So connect these, make a DAC. Let's make an mc.ecdac. Turn on audio. Turn this on. You can see we have our grains in our empty buffer, which is great. One thing we'll need to do is make a Q metro. I'm just going to do it at 30 frames a second. That will bang this waveform. This will cause it to keep drawing the actual waveform. These are decoupled in the object, so it only draws the waveform once normally, because it can get kind of expensive if you do it too often. If you notice things are running in a laggy fashion, you can lower this amount. For me, it works fine at 30 frames a second. And just for testing purposes, I'm going to make a triangle wave at 500 hertz, connect it to the first inlet of record, which will cause it to record when I turn it on, and start that. And I have to put active 1. And now it's constantly recording. You can't really tell. Let me put that with do an actual sound file so it becomes a little more obvious. We'll do cello F2, which should come with Max, I believe. And press play. You can see it records it into the buffer. So I'm doing mc.mixdown to 1 channel. This will just combine all 4 grains. And pack, so we get it in both channels. And when we play this, we should just get a playback of the note. That is precisely what we get. So good, we're on our way to making this harmonizer. So what we need to control is the playback rate of our grains, which we can do using this rate message. So this is going to be a multiplier to the rate of playback. So by default, it is 1. Connect this box here to demonstrate. And if we go lower than 1, so like a fraction, we'll be slowing it down. If we go higher than 1, we'll be speeding it up. So if I set rate to 0, it's just not going to play. Sorry, there is a issue I had, and we have to make sure we put our grain phaser on, otherwise the grain will never refresh. See how these are? We have 4 grains now. That's what we actually want. It's hard to tell when they're at a low playback rate. So at 1, it'll play. At 2, it'll play up an octave. We're going to run into an issue here because it's playing above, or it's going past our right point. So when it loops around, you can kind of hear it. It sounds kind of bad. Do 0.5, it's twice as slow, so an octave lower, which will work without any adjustment to the delay time. If we want to be able to specify this in semitones, you can use this expression. So it's 2 to the power of a number over 12. And this will convert semitones to rate. So we're raising 2 to a fraction of something over 12. And that's actually how you calculate equal temperament. So now if I do make it 3, we'll go down a third. If I go back to 0, see that's to 1, and the playback is normal. So great. Now we need to figure out how to get that pesky issue of the grains going above the right head, or above is probably the wrong word, but past the right head. What we need to do, or the easiest way to do it, is to figure out when the grain ends, compare that to when the grain should end if it's going to stay before the playhead, and then set a delay based on that amount. So we have the delay message, which will allow us to set the delay. And we're going to do a quick expression here, so we can have we can set our grain size in milliseconds, which will allow us to do this calculation. So if we want to get milliseconds to frequency, we have to do the inverse of a number divided by 1,000. So in this bit here, we're converting to seconds, and then we're getting the inverse. So we're converting milliseconds to cycles per second. And then I'll create another float box here. And to get the difference, what we'll need to do is subtract the time of the grain from the time multiplied by the rate, or subtract the time of the grain from the time multiplied by the rate. So make another expression. It's going to be F1 times F2 minus F1. So we'll connect this here. Make a trigger float bang, or other way around, trigger bang float. So we're going to send the message and then cause it to output here. We want that multiplied by the rate. And for now, I'm just going to turn this off. And we'll just look at what numbers we're getting. So if our grain is 500 milliseconds and our rate is 1, or our rate is 1, so 0 transmission, we get 0 because they're going to end at the same time. We're not changing the rate at all. If I set this to 1, we'll get a positive number, so it's going ahead of the right point. If I set it to a negative number, we're going behind the right point, in which case we don't really need to worry about it. To deal with that, we'll make an if statement. We'll say if our number is greater than 0, then output the number. Get a $sign there. Else output 0. Connect that here. And then this is going to connect to our delay. So now, if I type in 5, we'll get our delay in milliseconds that we need. Let's test it, make sure it works. I did something wrong, because that happens. That does seem a little low. in milliseconds. And the issue is we are sending the rate over here. We need to send the milliseconds. It's my bad. And yeah, that seems like a more reasonable amount. So let's try that again. We can see we're not going over the read point right now, but it does count kind of artificial, a little bit funny. And we can fix that by adding a delay random. We're basically getting phasing artifacts and just adding like a little bit of random delay will get rid of them. So let's try 2 milliseconds of random delay. We're still getting some. Let's try 50. That seems like a lot. That seems to be a bit better. But it shouldn't need to be that high. Maybe something like 10. So great. Normally, I'll also set this a lot lower, something like 125. And you can see we're getting that pitch shift. So let's go an octave higher. 2 octaves higher. And as we go higher, we're going to actually want to make the grain size less if we're wanting to make it sound better for certain things. As we go lower, if we have a small grain size, we're actually not going to be able to hear some of the frequencies because they won't get represented properly. So it's going to sound better if we have a bigger grain size if we're lower. Though it will work with lower ones, of course. So let's also add some feedback, because that's one of the fun things you can do in a delay harmonizer, is you can add some feedback and then you get just interval cycles from that transposition. First, what we need to do is add a cross filter, and this is just to eliminate the low frequencies. We need to get rid of them because otherwise we'll feed our window back and we'll get this huge just like DC burst. That is bad and we don't want. So I'm actually going to have that go into our pack as well. And we're going to have tap in. Let's give it a max of 500 milliseconds. And then a tap out. We'll have a default to 125 milliseconds. And then we'll multiply it. We'll initialize it at 0. And then we just need to feed it back into our input. There. And I'm going to align this patch cord so it looks somewhat nice. All right. So it should just be normal, like before we do this. I'm actually going to do this something less extreme, like maybe -3. There we go. And I will change the amount of feedback that we're adding to something much higher, like 0.8. You can see we're getting a lot of lower frequencies. Let's do it higher. It might be easier to hear. See, we get a like diminished triad that just keeps on going up. We can make this number even higher. And we can get a cool little effect that way. We can do that, of course, with any number. So we get like a glissando that way. And if we go to really low numbers, it's just going to really fatten the sound. Which can be a nice effect. So I hope this was helpful, and next week we will talk about doing multi-voice granulate, or not multi-voice granulation, we're already doing that, but multi-voice harmonization using the same Grainflow object, while also using tables to define different transpositions for specific grains. Anyway, see you next week.